Hey everybody, Jason here, and I'm recording this video from Ny-Ålesund, Svalbard, the northernmost town in the world. If you've been following my science outreach postings, you'll know that I'm here for a couple of scientific rocket launches to study the upper atmosphere, but I'd like to explain in a little more detail what exactly we're doing and why. For starters, let's take a look at the Earth's atmosphere. For a sense of scale, here's Mount Everest, the summit of which is 29,000 feet high, or about 8.8 kilometers. Commercial airliners fly a bit higher than this, up to around 38,000 feet. A modern fighter jet like the F-22 Raptor has an operational ceiling of about 60,000 feet. Strong thunderstorms can have cloud tops up this high, but most clouds are lower than this. This bottom atmospheric layer, called the troposphere, reaches up to between 8 and 18 kilometers, depending on your latitude. Above it is the stratosphere, which reaches up to between 50 and 65 kilometers. Into the stratosphere is a saying that we use for way up there. Very few aircraft are capable of reaching the stratosphere, but there are a few. The SR-71 Blackbird, for example, could fly at 85,000 feet, and high-altitude balloons are capable of carrying a passenger up to about 130,000 feet. Most people think higher than the SR-71 is pretty high, but we're only getting started. Above the stratosphere is the mesosphere, reaching up to around 80 kilometers, and above that is a fourth region known as the thermosphere. The US military defines 80 kilometers as the edge of space, and any pilot that flies this high is awarded an astronaut badge. If you do actually want to send anything up this high, you need a rocket engine. The air is far too thin for air-breathing jet engines and too low density to support a balloon. In 1963, the X-15 rocket plane came up here to set a record of 353,000 feet, which stood until 2004 when the Spaceship One rocket plane flew to 367,000 feet. Both of these aircraft also passed what is known as the Carmen Line, an imaginary line at 100 kilometers altitude which is also often defined as the edge of space. But in reality, the atmosphere doesn't just end at some line, it continues, becoming less dense and less dense for quite a ways further up. Above here is where the aurora resides, from the pink-looking lower borders reaching just below 100 kilometers, to the green curtains from 100 kilometers up to just under 200 kilometers, and the fainter red upper reaches stretching more than 300 kilometers up. I mention all of this to give a sense of context. When we think of the atmosphere, we tend to think of all the stuff way down there, and the popular conception is that space is completely devoid of air. But even way up at 400 kilometers in the orbit of the International Space Station, there are atmospheric waves and tides, winds and day-night temperature cycles, particle ionization and recombination, and other physics and chemistry and all sorts of things happening. The air up here is certainly far, far too thin to breathe, but it does create drag on any spacecraft orbiting or passing through this altitude. That drag will eventually slow a spacecraft down enough that it falls back to Earth unless it can be periodically boosted to compensate. This makes it very important to predict just how much atmospheric drag a spacecraft will encounter as it orbits the planet. Now that we've covered the basics, let's get down to specifics. Earth-studying satellites orbiting at around 400 kilometers altitude have identified a region near the poles that we call an enhanced density anomaly. That's technical speak for there's too much air up there. The satellites can see a large blob of air, creating much more drag than expected, in an area known as the polar cusp. What's the polar cusp? Well, if we take a moment to look at the shape of the Earth's magnetic field, from afar it looks like the standard dipole shape that you've probably seen before. Magnetic field lines stream out of one pole, loop around, and come back in at the other pole. This creates a shield which blocks any solar wind flowing towards Earth. It catches those charged particles blowing off the sun and traps them, transporting them around to the backside of the planet where some of them are accelerated down to the atmosphere in a ring-shaped area near the poles. The particles collide with the atmosphere and create auroras, so we call this area the auroral oval. Except, what about this area right at the top? It's not protected at all. Solar wind can and does stream right down this funnel-shaped hole to hit the atmosphere. This is what we call the polar cusp, the area just inside the auroral oval, on the day side of Earth, where the atmosphere is directly exposed to solar wind. So this blob of dense air seems to be just hanging out in the polar cusp. It weighs enough that it should sink down lower in the atmosphere, but it doesn't. Why not? Something must be counteracting the force of gravity to hold it up, but no obvious balancing forces have been observed. It's a complete mystery. Well, that's what we're here to find out. We have a few ideas as to what might be supporting this density anomaly, and to test them we need to take measurements from inside the anomaly. And if you remember from earlier, the only way to actually get any equipment up to this altitude is to use rockets. So, we brought rockets.